I'll start. Okay, I think we're good to go. The Communications Hub hosts this event. My colleague, Helen Choi, and myself, Elizabeth Fife, are the co-founders of the Hub, which is a dedicated center for PhD students to get one-on-one help with all their critical writing and speaking projects, of which this is one of them. So welcome today. This is Viterbi's second 3-minute thesis contest. And today we celebrate the exciting research of the PhD students in this globally recognized contest. It takes place at over 1,000 universities across 80 countries. And the goal is building students' academic presentation skills specifically. So the experience is everything here. The effort to explain engineering research to varied audiences is quite the worthy challenge. And it's a great opportunity for our PhD students to share their work beyond their lab and their advisors and their other colleagues. So here are the rules. Okay, it's basically one static slide, 3 minutes max. The participants will stop at 3 minutes, no matter what, done or not. They need to cover background of their research, significance, results, outcomes, and impact of the research. Next slide. Yeah. The judging criteria consists of 2 basic categories. We have sort of content, which is significance, impact, that it's clear. And then the second is the delivery elements and just overall engagement, how well the talk is geared to a non-specialist audience, and that it's communicated with enthusiasm. So the idea is this is a valuable and fun experience for everyone here. So while taking part is of course its own reward and really the point of it, as a side, we have exciting prizes. So the winner will also be sent to the regional competition. So, but you know, as I said, beyond the prizes, it's the learning experience that's really invaluable. And participating in 3MT, it will add to the experience of each of today's contestants, who are all here to challenge themselves as public speakers in a wider forum. So I will introduce our esteemed 3MT judges here. We have Arturo Cajal, a PhD student in the Department of Aerospace and Mechanical Engineering, who was also one of last year's Viterbi's 3MT finalists. And we're waiting on our second judge. Maybe went to the wrong room. And our other judge is Gaurav Sukhatme, Executive Vice Dean, Endowed Chair in Computer Science and Professor of Computer Science and ECE. So with that, I think we are ready to begin with our finalists.
Tons of applicants.
Yeah, we had.
So you're the best.
Yeah, lots and lots of applicants this year. Okay, well, we will get going. Our first speaker is Ali Ghafelebashi, Department of Industrial and Systems Engineering. Yay, give him a hand. 6th year, a PhD student. Professor Maisem Razaviyang is his advisor, and his talk is Rerouting for Rewards, Easing Traffic with Incentives.
We all know the pain of LA traffic, spending 40 minutes on the 405 freeway to go 5 miles. Not fun. Many solutions have been tried, like expanding highways, but none have worked. In my project, we've got a solution. We're giving drivers incentives, like cash or coupon, to take the route that we suggest. Imagine this. You avoid the jammed 405 and get a Starbucks coupon for the route that we suggest, instead of sitting in traffic. Here, I know that everyone is not a coffee fan. That's why our model is personalized and picks the reward that is most likely to get you on board, like cash. Our setup is dynamic. It knows that you might feel different at different times of the day. Here's the cool part. We are offering incentives for taking the routes that might add some time to your commute. We compensate you for your valuable time because you're helping to improve the overall traffic. Including all these details makes the problem challenging to solve. We've designed an algorithm that breaks down the problem into smaller pieces and can use the CPU of drivers' smartphones to solve the problem efficiently. We're not just incentivizing individuals, but also companies like Uber or Amazon. Imagine this. Your Uber taxi offers you a discount for taking a detour. You're just chilling in the back seat, saving some bucks, reading your book, and helping to improve LA traffic. Why should companies hesitate to join? They're cautious about their valuable data. It's like treasure to them. We use advanced techniques to guarantee the privacy and security of their data. No leaks are allowed. Now, let's hit the road, enjoy some smoother rides, and get a bonus or two along the way. Remember, the next time you're stuck in traffic, you could be sipping on that coffee that you got for taking an alternative route. Cheers to traffic jams turned into coffee rounds. Thank you.
Nice job.
Yes.
Okay.
Hey.
Okay, our next speaker. I'd like to introduce Julie Jiang. Oop, we have people.
Stand here or back there?
Becky, up there is good, yeah. Okay, I'll just continue. Julie is from the Department of Computer Science, a fifth-year Ph.D. student. Her advisor is Professor Emilia Ferreira, and her talk today is Mining Online Human Behavior for Social Good.
Who here spends too much time on social networks? I do too, but at least I study social networks. Is this working? So I can tell people I'm working when I'm actually just scrolling TikTok. Hi everyone, I'm Julie. I'm a computer scientist who loves social networks. Social networks have completely transformed the way we connect with each other. But with it also comes challenges such as addiction, misinformation, cyberbullying, and a host of other social mental health issues. We can't escape social media, but my goal as a researcher is to understand more about online human behavior so we can promote the positive aspects such as positivity, generosity, or inclusivity, and mitigate the bad ones. Mining online human behavior for social good. My first contribution in my dissertation is a machine learning-based social network modeling method that leverages the brilliance of large language models with a simple exploitation of the social network structure. Without getting too much into detail, which you probably don't care about anyway, I leverage the concept of social network homophily, that you are more similar to the people around you than not. Birds of a feather flock together. And I applied my model to a range of real-world problems. Let me give you two examples. During the early days of COVID, I discovered that online COVID conversations were primarily driven by political partisanship, which led to the formation of online political echo chambers, which just might explain why we have so much misinformation and radicalism about COVID online. In another example, I wanted to find out why some people are so toxic online, which is a very pervasive issue plaguing society. And I found that a lot of the haters were not as much driven by the desire to attack the poor victim, but because they want a validation and social approval from their network ties. Essentially, online toxicity is almost a socially motivated behavior. And by understanding that, we can design intervention and moderation strategies to effectively combat online hate speech. If there's one thing my dissertation accomplishes, I hope it is this, that instead of viewing each one of us as isolated individuals, let's recognize ourselves as interconnected social beings. Our behaviors are all linked to and possibly influenced by those around us. And I hope that researchers like you, policymakers, leaders, can tap into the vastly underutilized potential of social network data and mine online human behavior for social good. Thank you.
Nice. Okay, great. Next up, our third speaker is Shilpa Vijay from the Department of Aerospace and Mechanical Engineering. Shilpa is an 8th-year Ph.D. student. Her advisor is Professor Mittal Luhar, and her talk is Turning Up the Heat and Turning Down the Drag with Porous Magic.
In the figure to your left, you can see Harry Potter about to jump into his invisibility cloak to become invisible. If you want to design an invisibility cloak in real life, you would need a material that manipulates the path of light in such a way that it reflects whatever is behind Harry and hence ends up hiding Harry himself. Inspired by this philosophy of manipulating the path of light, my research focuses on using porous surfaces to manipulate the path of fluid flow. And here we want to focus on two applications. Can we reduce the friction experienced by a flow that goes over a porous surface? And can we enhance the heat that is transferred through the flow over the porous surface? In the figure to your right, you can see that as a fluid approaches a porous surface, it results in fluctuations in the path of the flow over the fluid. A key property of the porous medium that causes these fluctuations is its permeability. It is its ability to allow the fluid to go through it. Higher the permeability, less is the resistance that a fluid experiences over a porous surface. I manufactured multiple porous surfaces with varying permeabilities by varying the porous microstructure in all three directions. And then I put them together in an experimental setup to measure temperature, pressure, friction resistance, and visualize flow structures over a porous surface. There were two key findings. The first one, that if you increase the permeability of the material, it leads to a tortuous path for the fluid and then results in the swirling motion of the fluid, which enhances the heat that is transported by the fluid. And this has applications in electronics cooling solutions. The second thing we notice is that if you manipulate the permeability selectively in the directions of the flow, you can develop surfaces that experience less resistance to flow. And imagine what would happen if a large-scale structure like Boeing 787 is covered with these porous surfaces. Imagine the fuel efficiency gains we can achieve. Hence, my research shows that it is possible to manipulate the path of the fluid that goes over a porous surface. And by leveraging fundamental principles of fluid dynamics, we can achieve many engineering applications. And we can get one step closer to achieving invisibility cloaks for fluid flow. Thank you.
Yeah, right to the time. Yeah. Hi, okay. Here's your mic. Ah, mic up. You can actually just leave it behind you or stick it in your pocket.
This is good. I don't
Yeah,
know.
it's good? Okay. All right. Next up, our speaker number 4, Juzheng Liu, Department of Electrical and Computer Engineering. He's a 5th-year Ph.D. student, and his advisor is Professor Mike Shuowei Chen, and his topic, or his title of his talk today, is Making Integrated Circuits More Sustainable, Affordable, and Accessible.
Thank you. Hi, everyone. My research is about integrated circuits, or ICs. They're used in all aspects of our daily life for data acquisition, transmission, and processing. ICs are the brain of electronic devices, from your personal laptop to the cloud servers. With the emergence of new applications such as AI, quantum computing, and Internet of Things, the world needs more circuits with better performance and ideally lower cost. You might know the famous Moore's law, which states that the number of transistors and the performance of an IC double every 2 years. Nevertheless, you might also know that the Moore's law is dead, which means nowadays it is not so straightforward to further increase the circuit scale. This is mainly caused by 3 problems. The first problem is the unsustainable high power consumption. For instance, a single server group from Amazon can consume the power of 25,000 households. The second problem is the exponentially increasing circuit fabrication cost. To give you a feeling, a silicon wafer from the most advanced 3nm technology, which is just the size of your palm, can cost $20,000. The third issue is the unaffordable circuit design cost for cutting-edge ICs. For instance, the R&D of the new CPU from MacBook cost Apple around $1.5 billion. To solve those challenges and keep the Moore's law alive, my thesis focused on innovations of circuit architectures and design methodologies. As you can imagine, what happens in an IC is that the circuit components are continuously manipulating and measuring electrical signals. To measure those signals more efficiently and quickly, I came up with an architecture that can measure those signals by converting those signals into a time interval. As an analogy, please think of the scenario that someone is trying to measure the height of a cliff. Instead of directly measuring the height using a ruler, you can try to drop an object down the cliff and count the time it takes to reach the bottom. With this technique, I designed and fabricated a few circuit prototypes and demonstrated record-high power and cost efficiency. On the other hand, I also spent significant efforts on developing circuit design tools to reduce the design cost. The main idea is to build an AI core that can help human designers deal with the rigorous circuit design process. I developed a few algorithms to help the AI learn the circuit knowledge and optimize the circuit. I also built a complete design automation tool that can automatically perform circuit design tasks and generate the final circuit design according to the user request. I verified this flow using a few circuit design examples, and the tool can successfully reduce the design time from a few months to a few days. With those innovations in the circuit architecture and design methodologies, I'm making integrated circuits more sustainable, affordable, and accessible. Thank you.
All right, next up, speaker 5. We have Nikhil Chaudhari from the Department of Biomedical Engineering. Nikhil is a third-year Ph.D. student. His advisor is Professor Andre Irimia. Got that right? And his talk is Effect of Industrialization on Regional Brain Volume.
With advances in the developed world, we see, with advances in modern world, we see that our lifestyle has changed a lot. With the coming of modern technology and industrialization, our lifestyle has become more sedentary, our food more processed, and our social connections more distant. Now, I study brains, and we already had a talk about social networks, and all I was wondering was, how does social networks affect brain volumes? So brain health is a hard quantity to quantify. So what are we going to do? Are we just going to look at brain volumes? Well, exactly. I looked at brain volumes for a population that lives a lifestyle similar to our pre-industrialized ancestors. This population is known as Tsimane population. This Tsimane population is very special because even today, they live a lifestyle similar to what we had before industrialization. So we got brain volumes, and we compared how the brain volumes change with age for these Chimane population with a sample from the United Kingdom. The sample from United Kingdom serves as a reference population, which can represent all of us. The figure behind me in the first two rows show how the brain volume changes with intensity of color, telling how fast the brain volume changes. The last row compares the two populations and shows only significantly different structures in the brain, with blue structures showing how fast the brain volumes are going down for UK people compared to the Chimane people, and the red regions show the inverse. First of all, in the first row, you can see there are a few red regions, which means that the Chimane people show increases in regional volumes for these structures. This effect has not been observed in any other human population. Secondly, we see a lot of blue when comparing males, telling us that the Chimane males show slightly slower rate of brain volume decline compared to the UK people. And for females, we see a lot of red, meaning Chimane females are showing brain volume declines that are faster compared to the UK females. If you want to have a discussion about this, welcome. We should discuss this after the talk. In conclusion, modernization may not protect men's brain health, but they do seem to protect females' brain health. Thank you.
Glad I'm a female. It's worked out, huh? Okay, next up, speaker number 6. We have José Ferreira. Fans. Department of Astronautical Engineering. Second-year PhD student. Advisor is Professor Joseph Wang. And his talk is the atmosphere our trash can for satellites?
Well, hi folks. Welcome aboard. Please join me in this short trip around our planet. You're now sitting in a very particular place, a vantage point of view to our home. And I hope that these little cracks and dents you see over these windows don't really obstruct your view. This is actually the consequence of collisions between leftovers of small satellites and rocket bodies with our space station. These pieces of garbage essentially just stay in orbit for a long time, and they may hit us very fast as a bullet. As you may imagine, this can be catastrophic, right? So what's the actual solution for this? Well, we can just basically bring all this stuff down, all the remaining satellites down, and they just burn in the atmosphere. It's pretty simple, right? Well, not so fast. So the thing is, in fact, atmospheric re-entry reaches very high temperatures, and basically small satellites mostly completely incinerate, they completely burn upon re-entry. The thing is, by doing this, we are now injecting anthropogenic sources of potential pollutants in the atmosphere, and we don't really know the consequence. We know that, for example, aluminum oxides may be climate change potentiators, and they may even deplete ozone. So my job here is trying to determine whether these influxes are high enough for us humans to worry about it. What I'm doing here is using a model that developed in this school, USC Viterbi, and I'm also using our supercomputing resources to quantify the byproducts that are generated through this anthropogenic re-entry in the atmosphere. So what we actually do is we simulate how these atoms recombine during this super hot stage of re-entry, and this will hopefully tell us whether these byproducts are friends or foes. So far, we were able to estimate that only last year, 50 metric tons of man-made aluminum oxide were injected in the atmosphere. And this may take up to decades for us to feel the consequences of it in terms of environmental polluting. So as we prepare to disembark from this short trip, I want to leave you with a very resonating message. Be mindful about our spaceship Earth, and do share those principles. That's what Melissa, a NASA intern, did after learning a little bit more about my work. And she came up with this image, one that made us all travel today. I hope you enjoyed the trip. Thank you.
Okay. Speaker 7, Kicho Yu, Department of Computer Science, is a second-year PhD student. His advisor is Professor John Heidemann. His talk today, how to share internet data without compromising privacy.
How do we share internet data without compromising privacy? How can you kill two birds with one stone? My research answers this question. IRB, Institutional Review Board, banned sharing internet data in 2000 to protect everyone's privacy. This decision is good to protect privacy. However, this decision is not good, particularly to network researchers like me and network engineers. Because of the lengthy review process of IRB, network researchers use the synthetic data, which imitate the actual internet data, but that cannot fully represent the reality. Then how can you share the internet data without compromising privacy? Well, I have good news. Unlike 20 years ago, we have encrypted system. Most of the data in the internet are encrypted. So with encryption, we can share without compromising privacy. We propose a tool with randomness. Encrypted data has high randomness that no one can really understand its context. And this concept of randomness is called entropy. We used 3 different data sets for our experiment. First is my data set. Second is B-root data set from USC ISI. And third is NetBrain IXP data set, which we don't have access yet because of the lengthy review process for a year. Some of this data contain sensitive information, such as my personal credit card information or a chat history of my potential date. So I want to protect my own privacy. And I want to protect your privacy too, because I'm a good researcher. Trust me. So based on the subset of the first 2 data sets, we found that we can share about 90% of the internet data thanks to encryption. With this preliminary result, we are convinced that we can share the majority of the internet data. Imagine a world that you can instantaneously upload your video to YouTube, like the length of an hour longer video, but without revealing where you're located and what device you're using. Network engineers will enhance the internet speed and security. And with the help of the actual internet data, they can do their job better. Let's make the world a better place with a safer and a faster internet. Thank you.
Someone can take this seat here if you're people in the back. There's one seat if you want. All right, next up, we have Haixu from the Department of Civil and Environmental Engineering. He's a 4th-year PhD student, and his advisor is Professor Ximeng Wang. And his talk today, Creating Materials That Grow on Their Own.
Okay, so hello everyone. Do you know that our daily life can inspire us to invent new materials? Here, my research study is one of the examples. So one day, when I was doing my regular workout in the gym, Liang Center, the workout process attracted my attention. So I was thinking why our muscle can become bigger and stronger after its initial painful strain due to exercise. And maybe we can create something with similar functions. So as a researcher, I dived into the mechanism of muscle growing, so as shown in the top figures. So first, our muscle tissue is composed by many tiny fibers, known as myofibers. So when damaged during the training activity, these myofibers will awake a special cell called satellite cell spring into action. And then these satellite cells will attach to the damaged part and trigger the new growth of myofibers. So in the last figure on the top, we can observe there is a new grown layer around our muscle tissue. So this process can first repair the damage caused during the training activity and then make our muscle become bigger and stronger. So this interesting finding sparked an idea. Could we mimic the repairing and strengthening behavior of our muscle on manufacturing materials such as plastic and rubber? And here, what I want to tell you is, after a long journey of trying, we find a method to enable our materials to grow on themselves in response to force and deformation. And here is how it works. So first, we embedded some special chemical groups within our materials. So let's call them DABBF groups. So when force is applied on the materials, and materials start to deform, the bond within DABBF groups will break and release two radicals. And the most amazing thing here is these radicals are highly active. They can trigger many different chemical reactions, which means just by immersing the stressed materials inside a specialized chemical solution, the chemical reaction can be triggered by these radicals. So the surrounding molecules in the solution will react with each other. So they will connect and form a big network. And we can observe the liquid phase solution will solidify into a new solid layer around our materials. So just like what our muscle did before, the new ground layer will first repair the damage caused before and then make our materials become stronger. And of course, this can elongate the service life of our materials. So thank you.
You made it. Good job. Yeah. Alrighty. Speaker 9, we have James Yu from the Department of Biomedical Engineering. And James is an 8th-year Ph.D. student. His advisor is Professor Ellis Meng. And talk today, fewer connections make better brain implants.
Okay. How are memories formed? That is, how do the neurons in our brains form complex networks turning short-term memories into long-term memories? And if neurons communicate with each other using electrical signals, can we record those patterns? Can we decode those patterns? These are the sort of questions neuroscientists want to study. And the best way to get clear signals is by implanting long, needle-like probes that can record those electrical signals. Now today, the most advanced of these devices has a little over 1,000 recording sites, or electrodes as we call them, on a single probe. And you might ask, well, how does a researcher deal with like 1,000 wires coming out of a rat's head? Well, some of these devices are made of silicon. That's the same material our microchips are made of. So silicon devices can have advanced circuitry built directly onto those probes to process those many signals into just a few communication lines. But here's the bad news. Silicon probes are so much stiffer than the brain that within a few weeks, scar tissue forms around the implant, driving neurons away, degrading the signal, and eventually causing the device to fail. Now, one way we can reduce the body's immune response and obtain long-term recordings is by using flexible polymer probes. Now, this flexible technology is a bit newer than silicon, so we're just now seeing the hundreds of electrodes per device. And so you might ask again, like, how do researchers deal with 100 wires coming out of a rat's head? And the answer, unfortunately, is just a lot of time and labor, mostly grad students and postdocs, of course. So that's where my research comes in. what if we could combine the flexibility of polymer probes and the advanced circuitry of silicon microchips? Well, bonding these things together presents a couple of challenges. First, the connections have to be close enough to accommodate the chip. And secondly, the method can't be so hot that it degrades the polymer. And so to do this, I invented my own bonding method, and I compared it to a couple of industry standard methods and found that it performed rather well on test devices. And after some refinement, I took this 66 electrode polymer probe and a neural recording silicon chip and bonded those together. And when I compared this chip integrated probe to a passive polymer probe, I found that the performances were nearly identical, except instead of having to connect 66 wires, my device just needed 10. This technology will enable next generation long-term devices so that neuroscientists can one day tell us how our memories are formed. Thanks.
All right. Next up, we have James Croughan from the Department of Aerospace and Mechanical Engineering. And James is an 8th-year Ph.D. student. Advisor is Professor Alejandra Uranga. And his talk today, tubercles, sorry, did I say?
Tubercles.
Tubercles, thank you. Why you might add knuckles to your wing.
Hello everyone, my name is James and I'm here to tell you why you might want to add knuckles to the front of your wing. So let's start with the basics. What is a tubercle? A tubercle is what happens when you continuously deform the leading edge of a wing, leading to something that looks like knuckles. If you look at the image in the top left, that's what one of my wings looks like. The bumpy bit is the front. There's a few different ways to make those, but they all revolve around starting with the baseline airfoil, as you can see in green in the diagrams just below that, deforming that in some way into the red or blue ones, and then putting all of those together to form a continuous wing shape. So why are they interesting? So previous researchers have tried to put tubercles on wings with the goal of improving performance to varying degrees of success. Sometimes they've worked, sometimes they haven't. The problem is we don't really know how they work. So when we've tried to make them work, you can't always make it happen. So my research has focused on developing a comprehensive theory behind how tubercles function with the goal of enabling design improvements. So previous research has shown the existence of a couple different mechanisms. In the bottom left image, you can see green and red spirals. Those mechanisms are well understood. My new mechanism is the one drawn in blue. So what I've studied is how that mechanism works, as well as how you can design a wing to take advantage of it. So what I found is in the images shown in the middle. So these images are basically, if you look from the back of a wing towards the wing, and then these are flow diagrams. So they show how the flow is moving. The top surface of the wing is at the bottom of each image, and where the tubercles are located is drawn in the plot on the bottom. So if you look at the plot on the bottom, you see there's a peak. Look directly above that, and you'll see that there's a section that's green just to the left of it, and a section that's pink just to the right of it. Now green in that diagram means the flow is moving to the right, and pink means it is moving to the left. So that means that that flow is actually moving towards the pointy bit of the tubercle. That's important because it allows the flow to loop up and around, as you can see in the diagram just to the right of that, which shows the active formation of a bubble. Now, those bubbles are important because they enable large performance enhancements. So moving to the far right set of diagrams, on the top, we have lift. So lift, you always want more of in a wing. That's a good thing. My wings are shown in color. So anything that's colored is using my design method to add tubercles to it, versus the gray one is a baseline, which is flat. So you can see the tubercled wings all have much higher lift than the baseline one, which is a good thing. Likewise, the middle plot is drag, where you want less. My wings are all the same or better than the baseline wing. And the last plot is lift efficiency, where more is always better. Again, my wings are the same or better than the baseline wing across the board. And that is why you might want to add knuckles to the front of your wing. Thank you.
Okay, we're up to speaker 11. We have Sina Aghaei Department of Industrial and Systems Engineering, 6-year PhD student. Sina's advisor is Professor Phoebe Vallanos, and his talk today, Analytics for Social Impact.
Okay, so hey everyone. Nowadays, across numerous domains, data collection is a common practice. And efforts are made to leverage this data to develop data-driven solutions to inform business decisions. And interestingly, in recent years, this trend is observed in high-stake domains where people's lives and livelihood are on the line. Consider a housing allocation for people experiencing homelessness, where being allocated a housing resource or getting denied of receiving one is a life-altering event. Similarly, in a hiring process, whether to reject or accept an applicant can profoundly impact their career. So as you can tell, not every data-driven solution is safe to be deployed in such critical domains. Certain characteristics need to be considered. One, we need interpretability, because the policymakers, the people that are affected by the policies, they have this right to understand the rationale behind the decision that we make. No one should face denial of receiving a vital service like a kidney transplant for some unexplained decision made by a black box algorithm. Secondly, we need optimality to ensure the highest accuracy and performance and decision quality in a situation where even serving one extra individual is extremely important. And last but not least, we need fairness to avoid introducing new biases and perpetuating historical biases to our future decisions. But the issue is that designing a data-driven solution with such characteristics is not an easy task. In my research, I have developed predictive machine learning models to forecast a quantity and prescriptive policy models to recommend a certain treatment that prioritize interpretability, optimality, and fairness. And I have translated these theoretical contributions to practical application through our collaboration with Los Angeles Homeless Service Authority, where together we have crafted a housing allocation policy for individuals experiencing homelessness in LA, which prioritize these characteristics that I mentioned and is safe to be deployed. Our solution not only outperformed the current policy under deployment, but also is a testament to data-driven, interpretable, and fair decision-making. Thank you.
Okay. We're up to speaker 12. We have Bozhou Zhuang, Department of Civil and Environmental Engineering. Bozhou is a third-year PhD student, and his advisor is Professor Borat Gençtürk, and talk today, Ensuring a Safer World with Nuclear Energy.
When you hear the word nuclear, what comes to your mind? Nuclear radiation, nuclear power plant, or nuclear weapons? When my PhD advisor asked me to do research related to nuclear, my first response was, will I survive? Of course, the answer is yes, I'm still standing here. But my reaction is quite common, since we all know the severe consequences if the nuclear radiation gets leaked. But do you know that given the ideal conditions, there is less than 1 in 1 billion probability that the nuclear radiation would ever be leaked? The nuclear energy is also one of the cleanest, most secure, and efficient energy sources we have on Earth. A single uranium fuel pellet, as small as a fingertip, can produce as much energy as 17,000 cubic feet of gas fuels, 1,800 pounds of fossil fuels, or 150 gallons of oil with zero carbon emission. Currently, there are around 440 commercial nuclear power plants in the world to provide 20% of the world's electricity. So is nuclear energy the perfect solution for our humans? Unfortunately, no. Each year, over 10,000 tons of nuclear waste are being generated worldwide. They are called spent nuclear fuels and must be stored in these specialized canisters. The canisters may need to store the nuclear waste for up to 100 years because we just don't know how to recycle them. During a long time duration, these canisters are vulnerable to cracking, corrosion, or even mechanical damage. So these containers need to be inspected regularly, like we all need to see our doctors each year. But the canisters are sealed, hard to access, and operate in high radiation environment. So how can we do health check on these canisters if we cannot open them? My PhD thesis answers this question. I developed non-destructive evaluation techniques that integrate sensor technology with artificial intelligence. In our lab, I mounted ultrasonic sensors on a canister mock-up made of carbon steel to run experiments. The collected data were then processed using machine learning models to learn the damage patterns. With the aid of AI, we are not just identifying the damage levels, but also detecting any gas leakage that may result from the damage. It is promising that our inspection methods can help the nuclear industry to make judgments, and thus ensure a safer world with nuclear energy. Thank you.
All right. Speaker 13 is Kazen Bakian-Dogaheh from the Department of Electrical and Computer Engineering. Kazen is a seventh-year Ph.D. student. His advisor is Professor Madadin, and his talk, Understanding Arctic Permafrost Carbon Cycles via Radars.
Thank you. Thank you very much. So, hi everyone. I'm very excited to be here. I've been studying the radar and remote sensing techniques in the last few years. And if you know me at all, I'm always excited to just jump on an excited rant and talk about the radar, remote sensing, and how amazing these techniques are. But today I'm going to talk about this big elephant in my slide. And you've all probably have heard about the story of the blind and the elephant, which is really the moral of this story is about lack of sufficient data and observation can cause a large uncertainty in our estimate and guess. Now, this situation can apply in many other places, and one of them is my research, which is focused on understanding the permafrost carbon cycle. Permafrost is a frozen ground and is a dominant subsurface feature in the Arctic and northern high latitude. Many estimates says permafrost contains and stores the largest amount of soil organic carbon on Earth, which is currently frozen. But as global warming is happening and the temperature is increasing, this frozen carbon can release into atmosphere as greenhouse gases, which in turn can trap more energy and exacerbate the increasement of the temperature and cause a positive feedback. Currently, there is a lack of understanding and a huge uncertainty in the Arctic ecosystem, and we don't know whether the ecosystem in the Arctic is a source of carbon or a sink of carbon. Source of carbon is when the carbon released to atmosphere, and sink of carbon is when through photosynthesis and other processes, carbon goes back. Now, in 2019, a group in NASA asked 50 scientists that works on understanding the ecosystem in the Arctic and asked them what is the major cause and data gap that results in this uncertainty, because we don't know what is the current status, and we also don't know how the future would look like with all the global warming. Now, the result was we don't know the soil organic carbon. That's the main issue, and that's the main element in the subsurface. One way is go to the field and do measurement, but Arctic is a very vast environment. We talk about Alaska and also Siberia. Now, though fieldwork sounds fun, but it's cold there, and also it's a very vast environment, and access is very limited. So I'm an electrical engineer, and I design sensors. These sensors are called radar. They can be mounted on an airplane and fly over a vast area in the Arctic. By using radar measurements, I then use remote sensing techniques, which relies on the physics and electromagnetic, and I can come up with a very accurate map of the soil organic carbon. This soil organic carbon then can be used to reduce the current uncertainty that we have and project how the future would look like in the Arctic ecosystem. Thank you very much. That's my dissertation.
Hello? Okay. I'm a 6th year, I'm not a 7th year.
Oh, sorry. So Catherine Yunis, a 6th-year PhD student from the Department of Biomedical Engineering. Catherine's advisor is Professor James Finley, and today she's going to talk about why study balance with walkers.
At least 4 million people in the United States are prescribed walkers to help with balance, but there's an association of walker use with falls. Why do we care about falls? Why are people falling? How can we better understand this? What can we learn from the results? What do we expect to learn? And then what do we do next? These are the questions I'll be going through with you now. First, why do we care about falls? Well, beyond the fact that the device is failing the person when it's supposed to be helping them balance and not fall, falls can result in serious injuries. The leading one, which would be fractures when people go to the ER after falling while using a walker, and can even result in death. So it's very serious consequences. And why are they happening? Falls, the focus of my research is on answering the question, why people are falling while using a walker. And that's because in order to fix what's wrong, we need to first understand what's happening. We know that a common occurrence while using a walker is bumping into objects, like in the top left icon, like a curb or a door frame. And this is creating what's called a perturbation, which is an instability of balance. Perturbations can lead to trips or falls, and this may result in the falls that could occur and have the serious consequences. So if we know perturbations are causing falls, why aren't we studying them in the lab? Well, most perturbations occur in real life. So I've made a robotic walker that you see here. It's modified, which name is Folly. And that's meant to create controlled perturbations that we can use to study in the lab. These perturbations can be provided with different magnitudes. So that gives us an independent variable in our experiments. And the little dots represent motion capture markers that we can track while people move to use as a dependent variable of their balance. In addition, Folly can provide an independent variable of how much load people are putting on the walker. And that can be done by measuring with sensors in the legs and providing feedback through the headphones so people can regulate how much load they use. Why do we want to study loading if we're studying perturbations? Well, when people commonly walk with walkers, they may be using their hands and their upper body more than they're using their legs. So they might be putting more weight on the walker. We may expect, therefore, to see in a higher loading condition with perturbation that people, 1, might rely on the walker more for support. 2, they might take longer to recover from their balance after perturbation. And 3, they might be taking more steps to recover. They'd be stumbling for longer. These are some of the results that we would use to understand how people are losing balance and falling. And from there, as an engineer, I want to make a device not just that causes falls, but could improve people's response to falls. Thank you.
Great. Next up, speaker 15. We have Shihan Lu from the Department of Computer Science. And Shihan is a 6-year PhD student, and his advisor is Heather Culberson. And his talk today, Exploring Multimodalities with Touch.
Touch is everywhere and almost in every activities, from writing on the back of an envelope to the intense sports activities like climbing and bouldering. Touch interactions just play a significant role to ensure the task quality. And a subtle nuance in the touch sensations may completely change the way we interact with this world. And touch is quite different from the vision. First, touch is active, which requires active action to receive the physical signals from the environments. And the touch is also multimodal, different interaction types, and including like tapping, scratching, and also the different interactive mediums, either through a tool or through your finger, will completely change the way you feel the objects. And also, touch is also multisensory, which triggers the different signals during the interactions, including the force, tactile, and auditory feedback. And my work is pivoted around the interaction of the touch, which is basically twofold. First is how can we recreate these touch sensations in the virtual environments, which is shown in the orange boxes. And second is how can we equip the robot with the human-like or even superhuman touch sensing capabilities for the complex tasks showing in the blue box. For the first one, in the orange boxes, my goal is trying to model and render the high-frequency vibrations generated during the interaction with the textured surfaces. And then we combine the physics-based and the data-driven approaches for the texture modeling and incorporate the user's interactive motions for the real-time texture rendering. And this work has been embedded with the different interactive mediums, including the tool-based and also the finger-based interactions in the virtual environments. For the robot side, we focus on, we're trying to, currently the robot has quite limited abilities to sense, to get accurate state estimation during the context. And the games like Jenga and also the Kerplunk, these games are extremely hard for the robot to tackle because of the lack of the accurate state estimation in context, including the external context with the environment and also like the grasping point relative to the gripper. And to address this, we draw the inspiration from listening to the resonance after tapping the water cup, and we draw the inspiration from that and then propose the active acoustic sensing method to estimate the global object state from a local touch. And now we're combining the power of touch and the vision to tackle the challenging sensing problems in robot manipulation. And in the end, my goal is to realize to pair the research in the touch sensation, just like computer graphics and the computer vision. Thank you.
Nice job. That was good. Right on the... Okay, we're up to speaker 16, our final talk of the 3MT today. We have Yuanzhong Pan. Mic up, from the Department of Biomedical Engineering. And Yuanzhong is a 6-year Ph.D. student. His advisor is Professor Steve Kay. His talk today, Resetting the Timing Gears to Kill Cancer Cells.
My thesis is targeting a subtype of breast cancer by targeting the circadian clock. Timekeeping is very important for biological systems like ourselves, especially today because we have a running clock in there. The way we can keep time is because we have these small little clocks in almost each and every of our cells. This clock is formed by a group of genes called circadian transcription factors. And imagine them as gears in a clock, actual clock. And they will form a feedback loop, a delayed feedback loop that will give you an oscillator to make you know of time. And then these pathway is so important that it tells us when to eat, when to shovel the pizza that's stuck in there, and when to repair the DNA, and when to have an infection, have a response to the infections. Because they're so important in many of the basic cell processes, when cancer cell emerges, they can take use of these tools and put them in another way to fill their own needs. This is what shows in here. My thesis, the goal is to distinguish where does this happen. I focused on breast cancer, and in one subtype, breast cancer, in one subtype of breast cancer, this happens. And I discovered a strategy of using small molecules to target these genes. The significance is the big regulator here, they're so resilient, and they're not really targetable. So we use a different strategy of putting drugs in the body and hold the left and right arms, their wingmans, to hold this big valence in place so it won't do its job. So that's how we reset this clock in the cancer cells so it won't proliferate. And the development of these drugs took 10 years, and I spent my 5 years in the lab to build on this thesis and to discover how to use these drugs. And the next 10 years will be how do we move this modality down to the clinical path. And if there's one thing that I have time to tell you is listen to your clock and don't stay up late. And yeah, that's my talk. Thank you.
Okay, well, that wraps up our 3MT presentations. I think we should give a big hand to all of the presenters today who did a fantastic job. So it was a great display of Viterbi's, all of its research, and I learned a lot from brain space, a whole range of topics here. So right now we'll be tabulating, and you may vote for your favorite.
Enjoy some pizza as we add up all the scores.
Yes, pizza in the back, and
Yeah.
yeah. Start with People's Choice.
Yeah, the People's Choice is $500.
Yeah. Okay, our tabulations are complete. First, we'll start with our People's Choice winner, José Ferreira. Congratulations. You have a gift card too. Gift card coming. You can sit down. Should I start from the bottom? Okay, we'll start with fourth place. Fourth place, James Yu. Yay! Congratulations. Our third place finisher, Sina Aghaei. Second place, James Croughan. Congratulations. Our first place winner, Bozhou Zhuang. Yay. So great job, everyone. Thanks to our great competitors today, and thank you to the audience, and thank you very much to our judges. So this concludes.
Yeah, thanks very much.
Yeah, thanks.
And if you're a finalist or a winner, would come up and we'll take just a quick picture.
Some pictures, yeah.
Thank you.
Thank you.